Yeah, it's not so much about experimental techniques, but I can tell you about experimental techniques if you want. But I'm not, as many of you know, I'm not a great expert on multiaxial at all. I've sort of come here to learn, really. But we have done these experiments a few years ago, and we've been trying to think about what they mean and how they fit with predictions that you can make with different criteria. So I'm just going to give you a sort of overview of what we did and how we've been trying to analyse it, and then I hope that in the spirit of this meeting we could perhaps have a bit of discussion and you can tell me where we're going wrong. So that's kind of sort of where it is. So what we're trying to do is well, you know all that. We work a lot with Rolls-Royce, and in particular they're concerned about the disc of the aircraft engine, this disc here, and of course the stresses here are highly multi-axial, both in the web of the disc here, but also in the bore. They're quite complicated. There are thermal transients as well as mechanical loads and so on. We need, obviously, to we need to be conservative. We can't afford to have failures in service. We can test a number of these under reasonably representative conditions, but they're very expensive tests, and so we're limited. And therefore, you do need to base your life correlation to some extent on uniaxial test data that's extended into this regime. So that's kind of why we're interested in doing this work. And of course, most cracks initiate at the surface, certainly for the kind of lives that we're interested in here. The cracks will be surface initiated, so we're interested not in a fully multi-axial stress state, but just in a biaxial stress state, and therefore it's something that we can replicate in a test machine. And so we're interested in the pi plane, two principal stresses here, and if you think about what's going on, if you have a tension torsion machine, which is what most people use, or a lot of people use, you can investigate these two quadrants here, right? But actually, our discs are largely in this upper quadrant here on the web, and in the bore, they're sometimes here and they're sometimes here, depending on where we are in the cycle. So, although a tension torsion machine is in theory interesting, it doesn't investigate the very bits that we're interested in. And so one has to do a number of these cruciform type tests, Maltese cross tests, or you have to go to internally pressurized tubular specimens. So what we've been doing is investigating the use of these cruciform tests. They're not new, of course, but they're new to us. And they're manufactured out of a nickel alloy, waspalloy, and we've been trying to, we've subjected them to various different loading regimes and looked at the total lives, and then seen how we can correlate these. So the first thing we did was to do some finite element analysis. We wanted to do this because the load ratio that you apply is not the same as the ratio of the stresses that you see because of the specimen design, and it's not the same as the ratio of the strains, and so we did some elastic analysis. These are von Mises stress contours for different stress states, so that's an equibiaxial one, so equal tension in both directions. That's pure shear, so tension and compression. And this is a uniaxial equivalent. So this is where we are trying to achieve, in the middle, a uniaxial stress state. And then we did a little bit of plastic analysis. These tests are conducted just on the limit of plasticity. In fact, in general, we strain the specimen slightly just to work hard on it, and then we conduct the tests in the elastic regime, because that's what's relevant to the disc. One thing that's interesting when you talk about biaxiality is, of course, there are lots of different ways of defining the biaxiality ratio. So you can define it on the basis of load, or on stress, or on strain. And what we chose to do here was to define it on the basis of strain. And if you do that, you find, of course, that you've got 3 strains, and the ratio that you achieve depends on on Ito's definition. It's the largest of any ratio between the 3 principal strains. And if you take that, what you find is that you can't access a certain range of strain ratios, because effectively of Poisson effect. So, as it were, you can get -1 and you can get +1, that's okay, but there's a range in here between about, as it were, -0.3 and I think 0.6 that you can't achieve. Anyway, what we were given some guidance by Rolls-Royce. They wanted us to look at a number of particular states. So that what you find here is that's an equibiaxial, that one is pure shear, and then we have one which is uniaxial stress, and the other one which is a uniaxial strain state. And in particular, what they wanted to do, and this is on a peak stress diagram, the main series of tests that they wanted us to do was to do different biaxiality ratios with the same maximum stress. So we have here a uniaxial stress experiment with a particular value of uniaxial stress, and then they wanted us to do the same maximum stress but under equibiaxial conditions, the same maximum stress but under pure shear conditions, and then the same thing under uniaxial load. So now we've got a Poisson strain in the other direction, and the same thing here. This is the minimum von Mises, as it were. So here is where you're closest to a particular von Mises envelope. And then for some of these we did secondary experiments at a lower value of, so we did one here at a lower value of stress, and a repeat one here at that same value of pure shear, and then finally there's a final one here of pure shear. And these are lives in thousands of cycles. So here this one has a life of 154,000 cycles. This one 22,000 cycles. This one 58. And in fact, what you find here is that the longest life of these series of 5 experiments is this one here, which is carried out under uniaxial stress. For each one of these, and this is the thing that my current student Zhao has been starting to look at. So those experiments were done some time ago, but we've been having a look at them in a bit more detail. And in particular, we've been looking at things like where did the cracks initiate, what angle did they initiate at, and can we correlate these with existing parameters. So you see here, this is uniaxial load, so the load's applied in this direction. The worst, in fact this is strain here, but the worst strain is at the edge of the flat portion of the specimen, which is in the middle here. The cracks initiating just here, so just at the edge of this, here's the flat portion, and it's at about 45 degrees to the free surface, and so that is, I suppose, what one would expect. Here's biaxial load, so in this case the worst case is at the 45-degree position here, and that again is pretty much where the cracks initiate. The angle is a bit more difficult to tell. Here's the fracture surface and here's the free surface here. And this is pure shear. And again, the worst stress state here is at the centre of the specimen, or the worst strain state, sorry, is at the centre of the specimen. And here we have again, a rather complicated fracture surface. But the specimen, or the crack, initiated very close to that position of highest strain. So then, Zhao has been looking at a whole range of different criteria, starting with very simple things like range of von Mises or strain energy and so on, stress invariance, critical planes, and so on. And I just want to run through a few of these with you. I won't bore you with too many of them, but here's the von Mises. Well, clearly there's no real reason why this should be terribly good. But here you have different, this is, as it were, we're plotting this parameter against the number of cycles, and you can see there's a lot of scatter there. Interestingly, if you use elastic strain energy equivalent stress, the fit's a lot better, but we do have this one outlier here, and this is the low. This is a pure shear test at relatively low stress. So that's this one here, and then the rest of the results are plotted in a way that you might find slightly unusual. The point here is that we wanted to look at, as it were, this is one stress, and here is, or this is shear stress, and this is normal stress. So here we've got shear stress amplitude over reference stress, and this is some normal stress measure over the reference stress. So if you have a pure shear test, that would lie on this vertical axis here, and if we have a uniaxial test, then that would lie on this line here, and if we have an equibiaxial, then that will lie on this line here. And then what we do on here is to plot, as it were, contours of equal life according to the criterion, and then we see whereabouts our results lie. And this is, for example, Crossland's criterion, so you can see that this would be the 10 to the 4th cycle, this would be 10 to the 5, and this would be 10 to the 6th. And here we have, for instance, our range of experiments, and what we've done is we've plotted, as it were, on each of these radial lines, we've plotted where they are compared to those lines. So if the criterion were correct, then what we would have is something more or less parallel to these lines, and you can see that for these kind of lines down here, this is quite reasonable. But for the main range of tests, it doesn't fit terribly well, and in particular, we've got this maximum life here under the uniaxial stress criteria, whereas that's not being predicted by the criteria. And well, you get a rather similar thing with Findlay, but here these two lines collapse onto each other, so you don't actually, this quadrant that we had before has now I always do this. It comes with age, I think. That's my excuse anyway. But I know there are older people than me in the room. Yeah, so this kind of quadrant that we had before here has collapsed when we use that criterion. So the thing that's kind of interesting is that our experiments show that the maximum life should be on this line, and if you go away from that line, you should get a reduction in life. But in fact, the criteria seem to predict that, as it were, the life is reducing in this direction here. We had a look at some critical plane approaches, so Smith, Watson, Topper, and since Professor Sosi is in the room, it's a good job perhaps we had a look at Fatemi Sosi, but and of course this predicts critical planes, shear planes. The previous one predicts crack initiation perpendicular to the surface, and then this is a more complex Wang and Brown criteria. What happens when you look at the fatigue life predictions using this kind of criteria? Well, actually, Smith-Watson-Topper is not too bad, but of course the directions of crack initiation aren't the ones that are predicted with this. So it seems to be giving approximately the right lives, but it's not giving correct predictions of the orientation, and we have got a couple of non-conservative results up here. Fatemi Sosi is all conservative, so that's good, but there's quite a bit of scatter, and Wang and Brown is kind of all over the place. It seems to combine the worst features of both of those. So that's about it really. Elastic strain energy is probably actually the best of what we've got, but it's not terribly intellectually satisfying, I don't think. The stress-based critical plane models give similar prediction, but none of them was able to predict the fact that this was the longest life. The critical plane approaches in general give poor predictions outside this tension torsion region. So what we think is happening is most of these are calibrated from experiments in the tension torsion region, and because not so many people do the biaxial test, we don't have criteria, or a lot of the common criteria don't work terribly well in that region. SWT, as I said, was good in terms of lies, but not in terms of predicting crack initiation. And so that's where we are, and I'll be interested to get people's comments and advice. So thank you very much.